we can show the ground state space function by means of spin diagrams. In that example, we had a 1s orbital for both electrons. So we show it by means of a dash. And then the spin function must be antisymmetric, which means the ms must be 0. So if one of the electrons has an up spin, the other electron must have a down spin. This diagram, we can draw only one diagram. This has ms equals 0, and therefore s equals 0. And for example, this not allowed. Two electrons with the same spin in the same orbital. This is forbidden. So no triplet can be formed if we use 1s orbital for both electrons, like from 1s to electron configuration. In such diagrams, you may also obtain the ml value. ml for the first electron is 0. It's an s orbital. For the second electron, it is also 0. So 0 plus 0, you get 0. And this also tells you that L value must also be 0. So this is another way of describing what we did before, but using spin diagrams. Sometimes I'm going to use spin diagrams to explain the situation. Let us now consider excited electronic states. Helium atom. We are interested in the lowest few excited states. So in the orbital products, we take for one of the electrons 1s and the other 2s orbital. In terms of the products, orbital products, this is electron configuration. One orbital product is this. But because electrons are indistinguishable, we may take 1s for the second electron and 2s for the first electron. So we may write this as 2s for the first electron and 1s for the second electron. These are two different products here. They do not satisfy the requirement individually. They do not satisfy the requirement for being either symmetric or antisymmetric with respect to electron exchange. If you in the first product, if you exchange 1 with 2, you obtain the second function, but this function is a different function. All right. On the other hand, for singlet states, the spin factor is antisymmetric. Therefore, the space part must be symmetric. Similarly, for triplet states, the spin part is symmetric. In this case, the space part must be antisymmetric so that Pauli exclusion principle applies. Now, using these two product functions, we can construct new space functions which obey the requirements by taking linear combinations. Similar to what we did with the spin functions, we combine this product with that product with a suitable coefficient so that we have this 1s times 2s plus 2s times 1s. Here electron labels are 1, 2, and 1, 2. I have omitted the parentheses here, but the order of the orbitals from left to right, the first factor contains electron 1 label, second factor contains electron 2 label. This expression here is symmetric with respect to electron exchange. If you exchange 1 with 2, it is equivalent to exchanging the orbitals in the product. Exchange 1s with 2s, 2s comes here, 1s goes to the other part, and also here, 2s goes to the other part, 1s comes, becomes the first factor here. The overall function is symmetric, isn't it, with respect to, this is symmetric with respect to electron exchange. This will be multiplied with the overall normalization constant, C. Now, there is another expression in which the sign is minus here. This expression is anti-symmetric with respect to electron exchange. Remember, these are space parts. The overall function is space function multiplied by spin function. And the overall function must be antisymmetric. So what does it mean? The first function, this one, because this is symmetric with respect to electron exchange, what type of spin function should we multiply this function to obtain the total function? Because the overall function must always be antisymmetric. Pauli exclusion principle. If this is symmetric, we have to multiply it with an antisymmetric spin function. But the antisymmetric 2-electron spin function corresponds to which S value? 0. It's a singlet. This is on the other hand, the second function, this is antisymmetric with respect to electron exchange. We have to multiply it with a spin function which is symmetric in spin exchange. So which spin functions are symmetric with respect to spin exchange? There are 3 of them. They correspond to S equals 1, the triplet. Using spin diagrams, we may show this situation like this. represent each orbital separately. Say this is 1s orbital, this is 2s. Electrons are in different orbitals. So such a spin diagram is possible. Parallel spins. There is no problem in this case because the space orbitals are different. Other spin arrangements are, this is, if you write ms 1/2 plus 1/2, this is the total ms will be 1. There is a one of the electrons, in this case I have shown the second electron to have an opposite spin from the first one. In this case, what is the ms value? 1/2 plus minus 1/2, 0. But this diagram, instead of the first electron upspin, it is possible for the first electron to have downspin, but the second electron has upspin. This is also have ms equals 0. There are two such diagrams. And this is 1s, 2s. We also have both electrons have down spin. In this case, what is the total ms? Minus 1. So you see that 1, 2, 3, 4 spin diagrams. These are all different spin diagrams. The highest ms value is 1. If the highest ms is 1, what must be s value? S value must be 1. Now, if s is 1, what are the ms values, the total possibilities for ms? Ms ranges from s up to minus s in integer steps. If the s is equal to 1, there must be ms 1, 0, minus 1. Here is 1. Here is minus 1. But there are two zeros here. All right? We say that we make the following conclusion. One of these should correspond to ms equals 0 of s equals 1. The other one must correspond to ms equals 0 of another s value. But what should be the other s value? It can only be 0. One of them to ms 0 of s equals 1, this ms 1, 0, minus 1. The other to s equals 0. So in this case, both spins, both s equals 1 and s equals 0 are possible, allowed, if we select two different orbitals for the electrons, as we have outlined here. This one corresponds to s equals 0, and this space function can be multiplied with alpha times alpha or beta times beta, corresponding to these. And alpha times beta plus beta times alpha spin factor to produce the triplet stays. Now, as far as ML values, all of them are S-type. Therefore, all of them will have ML equals 0. If ML is 0, L has to be 0 also. So what are the term symbols in this case? These are also S-type. The first one is a singlet. The other is a triplet, S term. Remember, the ground state was also an S term. It was a singlet. So here in this example, you see that there is the ground state term symbol is the same as an excited state term symbol. It means that the energy you calculate using this expression will be larger than the energy you will obtain when you use this expression for the space part. So what we do is we number them. We say this is number 1. First singlet S term. And then this one is expected to be the next singlet S in increasing energy. So we will write this 2. And this one, for the triplets, this is the lowest triplet probably. So we would write first triplet S. So this way, the terms are numbered so that you know which one is lower in energy and which one is higher in energy. Now let us try to generalize these things to more than 2 atoms. And we start by introducing the concept of closed and open subshells. First, let us start with a subshell. A subshell is a group of orbitals with a given n quantum number and L quantum number. Energy depends on both n and L, but please remember that for a given L, there are 2L plus 1 ml values, and therefore there are 2 times L plus 1 orbitals in a subshell. This is the degeneracy of the subshell. So we can write it as degeneracy GL. Now, for a single orbital, according to the simple rule of Pauli principle, maximum occupation number of a single orbital is 2. If there are more than one orbital, then the maximum occupation of, when you imagine all orbitals in the subshell, then the maximum occupation number is going to increase. You can easily count it. If there are 2 times L plus 1 orbitals. Each orbital has a maximum occupation of 2. Then 2 times this number is the maximum occupation number of the subshell. For example, 2p subshell. How many orbitals are there in a 2p subshell? 2 times L plus 1. What is L for p? 1. 2 times 1 plus 1. There are 3 orbitals in subshell. Maximum occupation number of a 2p subshell is 2 times this number. So we may write N max for 2p subshell is 6. Similarly, what is the maximum occupation number of a D subshell? D means L is equal to 2. 2 times 2 plus 1, 5. 5 orbitals, each occupied by 2 electrons, means 2 times 5, 10. 10 is the maximum occupation number of a D subshell. Okay, now using this maximum occupation, if we have an electron configuration in which an orbital has maximum occupation number, we say that that subshell is closed. For instance, 2p6 electron configuration. Closed subshell. On the other hand, 2p3, 3 electrons in the 2p subshell, and 3 is smaller than the maximum. Such a subshell is called an open subshell. Okay, so first you should understand these concepts. What do we mean by subshell? What do we mean by closed subshell? What do we mean by open subshell? These are important concepts you should learn. Now, when you take any atom and write the electron configuration, you have learned how to write electron configuration in your general chemistry course. Then you can analyze the orbitals and you can partition the full set of orbitals into closed subshells and open subshells. Well, let us give a concrete example. Carbon atom, 6 electrons. One possible electron configuration is for the ground electronic state, 1s2, 2s2, 2p2. This is an electron configuration which is expected to produce the lowest total energy. Here we have a 1s subshell, a 2s subshell, and a 2p subshell. Next, we ask, are they closed or open? Here is the 1s subshell. what is the maximum occupation number of an s subshell? 2, because there is only one s orbital. So this is closed. Same thing is true for 2s, closed. But 2p, 2 electrons here. Maximum occupation number of a 2p subshell is 6. 2 is smaller than 6, therefore this is open. Open subshell. These are closed. Now, there are simple rules for determining total L value and total S value by looking at the given electron configuration and making some deductions from the electron configuration. Both L and S have no contribution from closed subshells. No contribution means these are numbers, of course. No means 0. For example, how many electrons are there? 6, 8, 10. Which atom is this? Which neutral atom has 10 electrons? Neon. It's a noble gas, isn't it? Now, closed shell, subshell, also closed subshell. What about 2p6? Closed subshell, isn't it? All subshells are closed here. According to this, L has to be, tell me, 0, and S has to be 0. No contributions from closed subshells. So any noble gas in the periodic table have closed subshells in the electron configuration. Therefore, all of them have L equals 0, S equals 0, or in terms of the term symbol, S, singlet S term symbols. For all noble gases. Because they have closed. Their subshells are all closed. And term symbol is singlet S. Now, let us now consider the more interesting case in which there is an open subshell. We are going to restrict ourselves to just one open subshell, or rather 2 electrons in open subshells. Let us call L1 and L2 be the orbital angular momentum quantum numbers of the two subshells because the closed subshells make no contribution to the total L, the only contribution to the total L and S value will arise from these two electrons in these subshells. The total possibilities for the total orbital angular momentum quantum number are, they are between, there is a maximum and there is a minimum. And if these are different, there are other values between L max and L min in integer steps. Here, maximum value for the total L is simply L1 plus L2, sum of these two. And minimum value is L1 minus L2. But you take it as a positive number, so this is magnitude. Here is an example. There are two electrons in the open subshell. For the carbon atom. So L1 is 1 and L2 is also 1. Both electrons in the same 2p subshell. So here values for the total L arising from this configuration. Maximum value is 1 plus 1, 2. Minimum value is 1 minus 1, 0. And are there other numbers between 2 and 0 in integer steps? There is just one value. What is that? 1. So these are the possible values for the total L arising from this electron configuration. And it has an open subshell, and there are just two electrons in the open subshell. Let us consider some more examples. Here is the open part, open subshell part of some electron configuration. It could be just this, in which case there are just two electrons, and we are talking about helium. But this could also be part of, open part of some more complicated many electron case. But we are assuming the remaining subshells are closed subshells. Here, L1 is 0, the L value for the first orbital, and L2 is 1. So maximum value is 1 plus 0. What is the minimum value? 1 minus 0, same. So there is just one L value here. It is L equals 1. Because the orbitals are different, now we turn into a total spin quantum number, S value. because the orbitals are different, one is 1s, the other is one of the 2p, 2p1, 2p0, or 2p minus 1 orbital. We may construct both singlet and triplet space functions so that s equals 0 and 1 are both allowed, so that the term symbols, possible term symbols are, all of them have p, capital P, corresponding to L equals 1. Both singlet and triplet P term symbols are possible. How many states are there? There are, the spin degeneracy is multiplicity, 1 for the singlet P. But there is space degeneracy, which is 2 times L plus 1. This is the space degeneracy. So for P, this will give you 3. 3 times 1 is the total number of states. So here we have 3 states. All these 3 states will have the same energy. What about in this case? From the space part, P, we have 2 times L plus 1, which is 3, times spin degeneracy, which is directly here, 3, which means 3 times 3, 9 states are degenerate. The total number of states arising from this electron configuration, 9 plus 3, 12 states. There are 12 state functions. These 12 state functions all arise from that electron configuration, 1s times 2p electron configuration. These 12 states are split in energy into 2 energies. The singlet energy is different from triplet energy. In other words, it's like this, in increasing energy. Calculation shows that triplet is lower in energy than singlet. So 2 different energies. Here we have 9 states. 9 states all with this same energy. And here we have 3 states. They have the same energy. Now, another example is 2p, 3p. In the open shell part, 1 electron is in a 2p subshell. The second electron is in a 3p subshell. Here, L1 is 1, L2 is also 1. But please note that one is 2p, the other is 3p. So different subshells. What is the maximum? 1 plus 1. And minimum is 0. There is also 1 here. So these are the possibilities for total L quantum numbers. Now, spin quantum number, total spin can only be 0 or 1, because there are just 2 electrons. For any 2 electron system, maximum value for S is 1. Number of electrons divided by 2 if n is 2 2 over 2 is 1. Next, we ask whether each spin S value can be used together with each L value. The answer is yes. And the reason is the orbitals are different. One subshell is 2p, the other is 3p subshell. So, since subshells are different, all combinations of S and L are allowed. In other words, from L, we have D, P, and S. This is the L part of the term symbol. Now we attach the multiplicity. We may take 0, which means multiplicity is 1. But S equals 1 is also allowed with these, all of them. So in this case, multiplicity will be 3. So we have 1, 2, 3, 4, 5, 6 terms. All arising from this electron configuration. Let us count how many states there are. What's the degeneracy of this term? L is 2 here. 2 times 2L plus 1 is the space degeneracy. 2S plus 1 is the spin degeneracy. The total degeneracy is spin degeneracy times space degeneracy. There is no spin degeneracy. It is 1, 1 here. So you just look at space degeneracy. D means L is equal to 2. So what is the space degeneracy? 5. Here, 3. Here, 1. Now, for this one, because now there is also spin degeneracy times space degeneracy, 3 times 5, 15. 3 times 3, 9. 3 times 1 is 3. Now, what is the total number of states? You just add up the number of functions in each term. 5, 8, 9, 12, 21, 36. Total 36 states. These 36 states all arise from this electron configuration. They occur in how many different energies? Remember, energy depends on L value and also S value. But energy does not depend on ML or MS. So each one of these term symbols that you see here means a different energy. So 1, 2, 3, 4, 5, 6 different energies. These 36 states occur in 6 different energies, and number of states at each energy is indicated by the numbers in parentheses. All right, let us stop here.